Today, I'm going to introduce you to another mathematical slash physics-based skill that's very important for the AP Physics 1 exam, but frankly is also very, very common in physics at large, and that is the idea of deriving equations. Now, to do that, we're going to end up looking at a particular situation. I'm not expecting you to be a master at deriving equations by the end of this video, but I'm going to introduce you to some strategies with this particular problem so that when we start looking at these sorts of things, you kind of have an idea of where to start. So let's start with the situation here. We have a wooden block that's at rest on a board. One end of the board is raised until the block is just about to slide. And this occurs when the board is at some angle theta sub max with respect to the horizontal. We want to derive an expression for the coefficient of static friction, mu sub s, between the block and the board in terms of given quantities and physical constants as appropriate. So what exactly does deriving an expression or an equation even mean? Well, essentially, it's asking us to complete a series of mathematical steps using known or provided equations, physical laws like Newton's laws, for instance, and specific conditions with the particular situation we're looking at to create some sort of final statement, saying blank is equal to blank. Now, previously, we would have gotten some specific number, like a is equal to 3 meters per second squared. But now, when we derive an expression or equation, we should be really just having a series of variables. So, for instance, a is equal to ft minus m1g over m1 plus m2. That's just an example. And why exactly do we want this more theoretical derived expression rather than a concrete value? And there's a few different reasons. One, this expression really applies to all scenarios rather than one specific one. So if I change my masses or my tension, I can quickly recalculate new values without having to go back and resolve the problem all over again. Two, it helps us look at the underlying factors in a given situation much more easily. So for instance, I could look at, well, if I change the tension, how does that change the acceleration? If I change one of the masses, how does that change the acceleration? Really make it somewhat like a proportional reasoning problem. And additionally, this will make it more clean and what we would often say in physics as being more elegant. And by clean, I mean that we don't have to worry about rounding. You know, you might get a slightly different answer with someone else when you actually stick in your calculator based on how you round your numbers, but we should always be getting pretty much the same expression or an algebraically equivalent expression for these derived equations. As for the more elegant point, one thing I want to mention is that whenever we have physical constants in these equations like g, you might be tempted to substitute in the number. So you might be thinking, well, g is 10 meters per second squared near the surface of the Earth, so we'll just do minus 10m1. We don't want to do that. We actually want to keep all these physical constants as the variables that they're written as typically. And that's largely because some of these change, for instance, in certain parameters. So g, that's what it is near the surface of the Earth, but maybe we want to look at the situation on the moon, and if that's the case, we would need to change g. So we want to keep it in this hypothetical form with all of the different variables written out explicitly. So what's the strategy we're going to utilize to derive expressions or equations? Well, there's not really a hard, fast, perfect way to do it. In fact, you kind of have to look at one situation at a time and try to really piece things together in a more creative manner. However, there are some things that we can do that will kind of help us put the pieces together so we can be a little more sure that we're going in the right direction. So let's go ahead and go through these all together with that particular problem we had earlier. So first off, we want to identify given and unknown variables that are in the situation, including relevant physical constants. So for instance, in the situation we were looking at this particular problem, the only given variables are one, we have some angle, theta sub max, and we have, a physical constant that we probably know applies here is g, the acceleration due to gravity. And that's it. Those are the only quantities we're given. And so therefore, our final expression can only be in terms of those quantities, which really limits what we can do. Additionally, our unknown is the coefficient of static friction, mu sub s. That's what we want to solve for. One final note I want to mention is that notice it says as appropriate, and what we mean by that is if there had been other variables here, it's possible that you wouldn't have to use them all in your final expression. You might be given more than you actually need. So it's okay if you don't always include every physical constant or variable or whatever. I will say in this particular situation there's so few, probably unlikely, but when we get more complicated situations, that very well can happen. So the next step is to try to identify potentially relevant equations. There's a couple of key ways to do this. One, by looking at the variables you have and the variables you want and thinking, okay, well, what equations use those variables? And two, looking at the situation at large and trying to think, all right, is there anything here that I haven't been thinking about that usually applies to these sorts of situations? So for instance, if I look at this particular situation again, I'm raising this up, I'm trying to find the coefficient of static friction. Well, there's a few things that pop up to mind. One, if I want the coefficient of friction, I probably want the friction equation, so that the static friction max is equal to the coefficient of static friction times the normal force. That's one I'm probably going to want. Two, odds are I'm probably going to need that the gravitational force or the weight is equal to mg. And additionally, because a certain situation is at rest, the block is just about to move, that means the forces are balanced. And so I really should be thinking about Newton's first law, or sigma F is equal to 0, not Newton's second law, which is sigma F is equal to ma. Those are probably going to be the ones I'm going to want to utilize. Now the next step doesn't always apply perfectly, but it's kind of good to try to identify an end game and work backward from there. And by that, what I mean is, okay, where do we really need to end up to make sure we get what we want? And then kind of think about, okay, how can I get there? So for instance, in this particular situation, well, what we want is the coefficient of static friction. So the only equation I have that utilizes that is the friction equation. So ultimately, I'm going to have to utilize this friction equation to get that coefficient, which means I need to solve for the friction force and the normal force. Well, how can I go about doing that? Well, we can start thinking, okay, this is at an incline. When if we dealt with those two forces of things on an incline, okay, sometimes we've done with the gravity force and the co-opponents, and that's probably the way we want to go. So we can kind of start to see where we should start and ultimately where we need to end. Now, the next points are really critical. One, we need to start with a known expression, a very explicit equation or physical law demonstrating that we are starting at a place that we know is true. We're not making something up. And then from there, to get to what we ultimately want, we have to make every step very, very explicit. I know many of you, frankly, like to skip steps because you're like, well, I can see that this is equal to that, so I'm just going to, you got to stop, and you got to write it all out. Deriving is a lot like proofs in math class, where you need to demonstrate where everything is coming from so you can totally say this final expression has to be true. It has to be the case. Now, additionally, there are some really useful things that you're going to periodically see in these. You're not going to always use these, but they will come up sometimes. One, you're going to sometimes have equations that have variables you don't know, but you'll have other equations that you can manipulate for those variables and stick back in. So you can substitute one expression in for another. Two, sometimes if we set two equations equal to each other, so let's say I've got a is equal to something and a is equal to something, I could set those equal to each other, and therefore I get rid of the a, and now I can start relating those variables together. And three, a lot of times you're going to see if there's some way you can cancel out variables. So like if you have a variable in a numerator and a denominator or some expression, well, we can get rid of those, and then we don't have to worry about that variable anymore. So looking at this situation, keeping in mind, we want to know, well, what is the coefficient of static friction? So if I manipulate that equation, we know this equation is true. So I can manipulate that for the coefficient, and I can think, okay, I need the static friction force and the normal force, and I can only do this in terms of the angle theta and constants like g. Well, we know how to relate these on an incline, but just in case we don't remember the details, let's go ahead and draw an FBD, and I went ahead and rotated my axes. And we see that the friction force, the static friction force, which is going up the incline, is balanced by the x component of gravity, and the normal force is balanced by the y component of gravity. Okay, well, if I need to figure out what these two pieces are, I need to basically now utilize Newton's first law in each dimension. So I'm going to say, all right, let's start off with Newton's first law in the x dimension. The sigma fx is equal to 0. Well, this piece here is Fg sine of theta. So Fg sine of theta plus the friction force equals 0. And that demonstrates to me that these two forces must be of equal magnitude. So I can stick in Fg sine theta in for that static friction force. Similarly, I'm going to try to substitute something in for the normal force as well by looking in the y dimension. In the y dimension, these forces are balanced. So we have Fg cosine theta plus Fn is equal to 0. And so I could stick in for the normal force Fg cosine theta because once again, those must have the same magnitude. So everything here has come from these equations over on the left. All right, so let's go ahead and now, substitute these two expressions in. So I have FG sine theta over FG cosine theta. Well, how can I simplify this? Well, there's FG on the top and bottom, so I can just cancel that out. And that leaves me with mu sub s is equal to sine theta over cosine theta. And this would actually be an acceptable version of the expression because I've reduced it to just the angle theta, and that's all I've had. Now I'm going to take it a step further because hopefully you know if we divide sine by cosine, we end up with tangent theta, and specifically, when this is that maximum angle, will be tangent of theta max. So this expression is a derived equation for the coefficient of static friction built from all of these different pieces. Now the last step we want to do is we want to double check to make sure that our derived expression only uses the quantities that we were given and very specific physical constants. If we're not giving it, well, then we can't use it. So looking back at the original situation, keep in mind we were told, well, we could use theta max and any physical constants, and we want to derive the coefficient of static friction, mu sub s. Well, our expression totally works for this. If you had some additional piece that included maybe like the mass or something like that, well, that would be a problem, and we would have to think about, okay, well, what can I substitute in or cancel out to get rid of those terms to make sure we are only with this. Okay, so this was an example of going through one of these derived and expression problems. We're going to be doing some of these in class together to get you a little more used to them. But make sure you go ahead and review the strategy and note anything that you think you're a little unclear of so we can try and answer those questions.